Hello class, this is Mr. Miller, and this is a video on the use of our understanding so that we can finish the endothermic lab process, or endothermic process lab. I noticed that there are a lot of people who really don't completely understand what endothermic process is and what dynamic equilibrium is, so we're going to go over it right here and right now. I have three slides, three pictures, screenshots from the link that Mrs. Levinson gave out to you guys. I gave it to you also, but I mean she's the one who posted it, and she found it, and it's a great description of what happens to ice and water when they're in dynamic equilibrium. So at temperature 0 degrees Celsius is when the phase change is happening between liquid on the right hand side, oops, sorry about that, and solid on the left hand side. That means that for every molecule of water that freezes, one molecule that's solid melts. It's in dynamic equilibrium. It's changing. Maybe in one instant, two water molecules, liquid water molecules, will freeze to solid, and only one will melt from solid to liquid. However, in the next instant, then usually it is a matter of two more molecules of solid water melting and one molecule of liquid water turning solid, freezing to ice. So that's what they mean by when they're talking about dynamic equilibrium. When anyone talks about that, it's a dynamic state, but at equilibrium they equal out to each other over time. Now, this dynamic equilibrium exists for pure water at 0 degrees Celsius. However, when you add a solute, and the solute can be anything, but when you add a solute, say sodium chloride or table salt, then things change. And it's still at 0 degrees centigrade. This system is still at 0 C. However, when you add salt, and there is any amount of liquid water, the salt can dissolve in the water, and it creates a barrier. It blocks the water molecules that are liquid from joining up with the solid water molecules to freeze. However, on the other hand, on the other side, the salt molecules that are dissolved in this liquid water do not stop the solid water molecules from melting to liquid. And so you get a shift in the equilibrium. And eventually, if you leave the system at 0 degrees Celsius and you've added a solute, such as salt, then all of that water is going to be liquid. It's going to be crashing into salt molecules. Every water molecule is going to be crashing into a lot more salt molecules than they are each other and freezing. And so the equilibrium is shifted. Now, this is a more molecular view of the same thing that I just showed you. And you can read this. The surface where ice and water meet is very dynamic. Molecules are always melting off and others freezing onto the surface. When the ice is stable, neither freezing nor melting, these two processes are happening, but they're in balance. They're happening at the same rate. The reverse is the same as the forward. If you reduce the temperatures, the probability of a molecule melting off will reduce, so the melting point slows down, or the melting slows down, I should say. And the freezing points, or the freezing speeds up, which means that the ice grows when it's below 0 degrees Celsius. If you heat it up in the opposite direction, the opposite will happen. The melting will dominate. So at 0 C, there can be the same number of water molecules joining up and leaving ice as there are joining up and leaving ice. That's what they're saying. So when salt is added, there's a lower concentration of water molecules in the liquid to come back and form ice. And so in this left-hand slide, you see two of the water molecules are joining the crystalline structure of the solid water. They're freezing. But there are also two that were freezing or frozen, and they're leaving that frozen crystalline structure and joining the liquid water. So it's an even keel. to join, to leave the solid ice structure. But when you add the solute, that solute acts as a barrier. And so, although they didn't illustrate any water molecules that are joining, I would say that this one probably would be the most likely to join up and become solid because it's at 0 degrees Celsius. And so really it could. But look, there are two water molecules that were solid that have changed to liquid. And all these other liquid molecules over here at the top of this slide are crashing into each other, but they're also crashing into the salt ions. And so those particles disrupt the crystalline structure of the water. And even at 0 degrees Celsius, that disruption results in liquid water more than solid water. So the dynamic equilibrium between solid and liquid water. For water, this equilibrium exists at 0 degrees Celsius. So for every one water molecule which freezes, a separate water molecule melts on average. But I put this without talking about water because it doesn't have to be water. We can talk about any kind of liquid that freezes or becomes liquid. So, and if you've got a solvent, or I mean a solute, in other words, if you've got a solute that you add to any of these solutions, it's going to change the equilibrium. This dynamic equilibrium is subject to change. And so, this solute blocks the solvent. Freezing needs less energy when there is a solute. In other words, freezing needs less energy. Let me stress that term, less energy. Freezing normally takes place in pure water at 0 degrees Celsius, but when you add a solute, like salt for instance, or table sugar, if you use sugar, it dissolves in water, doesn't it? But sugar is a different molecule than salt is, so it does disrupt the dynamic equilibrium of water. However, it does it at a different rate. It would take lots more sugar to disrupt the dynamic equilibrium of water molecules between solid and liquid than salt does. Table salt disrupts it very easily, and so you need like truckloads and truckloads of sugar if you want to spray it on the roads to bring the melting point down where people wouldn't have to drive on snow. They'd be able to drive on wet roads, or they can just use less truckloads of salt. It's a lot more money saving, and it's a lot more effective than the sugar is. The sugar would weigh a lot more. So, but the solute particles are barriers that block the liquid water from joining up again with the solid water, although they don't block the solid water from joining the liquid, the melting of the water. They don't block that. So the solid water molecules or particles are not blocked from melting by the solute particles, and so the total effect is that more and more solvent forms from the melting solid. And as I said, equilibrium changes. And so when you add your solute to whatever pure substance you have, whether it's water or any other liquid or solid, meaning ice, in dynamic equilibrium, the addition of a solute is going to change that equilibrium, and a new dynamic equilibrium is resulting. And so salt dissolved in water with one with significantly lower melting point than pure water is. However, if the temperature drops below the new equilibrium standard temperature, then the salt water solution will freeze again. So it doesn't completely disrupt the freezing of water. It just changes the dynamic equilibrium to a way lower melting point. But if you cross that melting point, then the salt water will freeze. So equilibrium depends on the amount of solute in solution, but there's only a certain limit depending on what solute you're talking about. However, if you have seawater, which is about 9% by weight or by mass salt, if you put like 20% per per mass salt water, that freezes at a significantly lower temperature than ocean water would. So seawater has a certain amount of solute in it, but if you add more solute, then the freezing point would go down from there even. And the more solute that you have, in other words, the lower the equilibrium that can be reached. So I hope you guys get this, and I hope you understand it. If you don't, please contact me. I've returned a lot of 2.10 labs with marks off because you guys aren't truly understanding what we're talking about as far as the ice cream and the salt water and the fact that the salt water is at a lower temperature. A lot of you think that salt water, the salt that you added to the water was taking away the heat, but let me tell you this. So keep this in mind. Even if I had salt and I put it in a deep freezer and got it cold as it would get, colder than the ice cubes that I would be adding it to, and I added it to those ice cubes, it would still break up. As long as the new equilibrium temperature would be, the temperature of the salt and the water or the ice that I would be adding it to were higher than that new equilibrium temperature, then the salt will melt the water, even though it may be even colder than the water is, as long as the resultant temperature, the temperature that you start out with, isn't so low. In other words, there are some days, especially in the northern United States, that are so cold that it doesn't matter how much salt you put on the roads. It doesn't melt the snow at all. And so this, let me go back to the first slide here. This equilibrium that we see is not disrupted when we add the solute. Now, 0 degrees Celsius, this solid water is disrupted. But let's say it's minus 30 degrees Celsius, or not Celsius, let's say minus 30 degrees Fahrenheit, which is something that happens in Alaska and the northern United States, Montana, and the Dakotas. These little water molecules on the right-hand side don't even break free from the solid. They're so low energy, and they are much more attracted to each other. They're not moving fast, and they'll stick together a lot more readily. And so you'll have a situation where there's salt on this side with no water molecules and water on this side with no salt. The salt may come into contact, but the contact that the salt would have just doesn't have enough energy to break at low enough temperature to break the water molecules off of the solid ice crystalline structure. So I just wanted to point that out. Let's see. So we're back here at this slide. This is the last slide, and like I said, if you guys have any questions, please call me or K-mail me, ask me whatever you want. But look at this video in order to improve your scores on Lab 2.10. Thank you.